Separately derived systems are defined by having their own source of power, such as transformers. In the scenario described, the 13.8 kV to 380 volt transformers feeding service panels in a separate building through isolation switches constitute a separately derived system. This is because the transformers provide an independent power source, the neutral is grounded at the transformer, and the neutral is not connected to the grounding conductor at the service panel. Regarding grounding the neutral busbar, according to the National Electrical Code, specifically Section 250.92 from the 2002 edition, it isn't strictly required to ground the neutral busbar again in the service panel for a separately derived system. However, it is generally recommended as an additional safety measure. This practice can further enhance the system's ability to handle fault currents and improve overall safety. As for linking the building grounding grid, it is indeed advisable to link the building steel structure grounding grid to the service panel ground. This interconnection establishes a continuous grounding path, which is crucial for managing fault currents effectively and minimizing potential differences between the two systems. By connecting the building steel to the service panel ground, a more robust and reliable grounding system is achieved. The recommended wiring configuration involves several key elements. Firstly, the transformer's grounded neutral should be connected to the grounding system at the transformer location. This connection ensures that the neutral is properly grounded at the source. Secondly, the service panel's neutral busbar should be bonded to the ground busbar via an equipment grounding conductor. This bonding creates a low impedance path for fault currents. Thirdly, the building steel structure grounding grid should be connected to the service panel ground, integrating the building's grounding system with the electrical system's grounding. Several additional notes are important to consider. Firstly, the equipment grounding conductor connecting the neutral busbar to the ground busbar should be sized in accordance with NEC section 250.122. This section provides specific guidelines for determining the appropriate size of the equipment grounding conductor based on the rating of the overcurrent protection device in the circuit. Secondly, the grounding electrode for the separately derived system should be located near the transformer, as stipulated in NEC section 250.30 ATWO. This proximity minimizes impedance and ensures effective grounding. Thirdly, it is crucial to ensure that there are no other grounding connections between the separately derived system and the utility system. Maintaining isolation between the two systems is essential for proper operation and safety. Let's delve deeper into the specific NEC sections and their implications. NEC section 250.9 addresses the use of grounding electrodes for separately derived systems, while subsection 2 indicates that a grounding electrode is not required at the service equipment for a separately derived system. If certain conditions are met, it is still generally recommended to install one for enhanced safety and performance. This is because a grounding electrode provides a direct connection to earth, which helps to stabilize the system voltage and provide a low impedance path for fault currents to return to the source. NEC section 250.122 provides the requirements for sizing equipment grounding conductors. These conductors are essential for providing a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protection devices such as circuit breakers and fuses. The size of the equipment grounding conductor is determined by the rating of the overcurrent protection device in the circuit, with larger circuits requiring larger grounding conductors. NEC section 250.30 ATWO specifies the location requirements for grounding electrodes used with separately derived systems. It mandates that the grounding electrode be located as close as practicable to the source of the separately derived system, which in this case is the transformer. This proximity minimizes impedance and ensures that the grounding electrode is effective in providing a low impedance path to earth. It is also important to consider the types of grounding electrodes that are permitted by the NEC. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The NEC specifies the requirements for the installation and bonding of these grounding electrodes to ensure that they provide effective grounding. In addition to the NEC requirements, it is also important to follow industry best practices for grounding and bonding. This includes using appropriate grounding and bonding techniques, such as exothermic welding or listed connectors, to ensure that the connections are reliable and corrosion resistant. It also includes performing regular inspections and tests of the grounding system to verify that it is functioning properly. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and industry best practices, electrical professionals can ensure that electrical systems are properly grounded and bonded, thereby minimizing the risk of electrical shock, fire, and equipment damage. Furthermore, it is vital to understand the importance of maintaining a low impedance grounding path. Impedance is the opposition to the flow of alternating current, and it is affected by factors such as conductor length, size, and material. A high impedance grounding path can impede the flow of fault currents, which can delay the operation of overcurrent protection devices and increase the risk of electrical shock. To minimize impedance, it is important to use short, direct grounding conductors and to avoid sharp bends or loops in the grounding path. It is also important to ensure that all grounding connections are clean and tight, as loose or corroded connections can increase impedance. In the context of separately derived systems, it is also important to consider the impact of harmonics in the grounding system. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads such as electronic equipment and adjustable speed drives. These harmonics can circulate in the grounding system and cause overheating, voltage distortion, and equipment malfunction. To mitigate the effects of harmonics, it is important to use properly sized grounding conductors and to consider the use of harmonic filters. Harmonic filters are devices that are designed to reduce the level of harmonics in the electrical system. They can be installed at the source of the harmonics or at the service entrance. In addition to the technical aspects of grounding and bonding, it is also important to consider the legal and regulatory requirements. In many jurisdictions, electrical installations are required to comply with the NEC or other applicable electrical codes. Failure to comply with these codes can result in fines, penalties, and even criminal charges. It is therefore essential for electrical professionals to be familiar with the applicable electrical codes and to ensure that their installations are in compliance. Continuing education and training are also important for electrical professionals to stay up to date on the latest codes, standards, and best practices. The electrical industry is constantly evolving, and it is important to stay informed of the latest developments. This can be achieved through attending industry conferences, reading trade publications, and participating in online forums. In summary, grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements, industry best practices, and staying up to date on the latest developments, electrical professionals can ensure that electrical systems are properly grounded and bonded, thereby minimizing the risk of electrical shock, fire, and equipment damage. Remember to always consult with a qualified electrical engineer or inspector for specific guidance on grounding and bonding requirements for your particular application. This narration provides a comprehensive overview of the key aspects of grounding and bonding, including the NEC requirements, industry best practices, and the importance of maintaining a low impedance grounding path. It also highlights the importance of considering harmonics and the legal and regulatory requirements for electrical installations. Hopefully this is useful for your educational purposes. Always be sure to consult the latest edition of the National Electrical Code and local regulations for the most up-to-date and accurate information. Electrical work can be dangerous and should only be performed by qualified professionals. When dealing with electrical systems, safety is paramount. Always to energize circuits before working on them, and use appropriate personal protective equipment such as gloves and safety glasses. Double-check all connections to ensure they are tight and secure. If you are not comfortable working with electricity, seek the assistance of a qualified electrician. Proper grounding and bonding are not only essential for safety, but also for the proper functioning of electrical equipment. A well-designed and properly installed grounding system can help to prevent voltage sags, reduce electrical noise, and improve the overall reliability of the electrical system. Furthermore, A properly grounded system can help to protect sensitive electronic equipment from damage caused by lightning strikes and other transient voltage surges. In addition to the technical aspects of grounding and bonding, it is also important to consider the environmental impact of electrical installations. Electrical equipment can contain hazardous materials such as lead, mercury, and cadmium. It is important to dispose of electrical equipment properly to prevent these materials from contaminating the environment. In many jurisdictions, there are regulations in place to ensure the proper disposal of electrical equipment. By following these regulations, electrical professionals can help to protect the environment and promote sustainability.